So welcome to part 2 of the presentation on the course Algebraic Structures. That is an online course that I am teaching to a very few students, and I'm delivering via this medium. And the textbook that we have adopted is this free textbook, Abstract Algebra by Thomas Judson, and supplemented by comments from Robert Beezer and Antonio Ben. So what we did in the previous presentation was, so this section that is a short note on proofs, and we just started talking about sets. So let us just continue with that. So for a set, we did not really start with axiomatic set theory, okay, because we are actually our first topic of course is the groups. So we are just going to informally think about a set that is a set, let me just say, may be thought of. Yeah, that might be better. Okay. So a well-defined collection of objects such that given any object, we can determine whether or not the object is in the set. Okay, so once again, we are just thinking of a set as a well-defined collection of objects such that given any object, we can determine whether or not the object is in the set. Now, some of the sets that we are going to use are, so first one being the very natural one, that is the set of natural numbers. They just evolved naturally. And so these are the counting numbers 1, 2, 3, 4, 5, and just go on and so forth. And of course, we can see that these are positive whole numbers in a way we converse, and 4 is a member of this set. 10, even though it's not explicitly listed, 10 is a member of this set. Say pi is not a member of this set, and if we want, then later on, let's just go through, since we talked about the natural numbers, just a natural evolution. I don't know much about history, but then, we had 0 coming along sometime, right? So these are the set of whole numbers. And then we can just go ahead and take z, the set of integers, just by taking negative of each of the natural numbers that we have. So these are the integers, okay? All right, and I think I'm only talking, not writing, even though YouTube is kind enough to automatically close caption, my videos, but it's still natural numbers, okay? And here we have, what are we going to call them as? Whole numbers, okay? And then we have integers, and then with the integers we can keep on forming. Say we go and write this set or make a new set, a divided by b, such that, okay, a and b are integers, okay? So a belongs to z, all right, and then b belongs to z, okay? B belongs to z, and then and b is not equal to 0, okay? So this is how we are defining rational numbers. So, and you can easily see that that n is contained in w, okay? So let me just take it like this, that n is contained in w, and w is contained in z, okay? W is contained in z, and z is of course contained in q. All right. So for example, any rational number, any integer, say 4, can be seen as 4 divided by 1, therefore is a rational number as well. Okay. Now let's just move forward with the set of real numbers, and let me just make it a little slightly dramatic here. Okay. So here we have the what you know as number line, and we can write, you know, 1, 2, 3, 4, our counting numbers, then put a 0, then plot negative numbers, and then now we got rational numbers. And notice that a number, once we take two rational numbers, anything in between is again a rational number. So we can start filling this line up, but it's not really completely filled up, because if we do this, that is, say, I mean, you can see we can have a lot more numbers, and you know that already, that is, that are not rational. Okay, so an example is right here. That is, let me get a perpendicular line. Let me get an intersection here. Okay, all right. So if I go ahead and take the circle away, and let's take this away as well. Okay, oh, sorry. Okay, let's just remove the perpendicular line. Okay, all right. So now notice this, that this is a segment perpendicular to the number line, which equals 1 in length. Okay, and then once that happens, if you do this, that is, construct this diagonal. So by Pythagoras theorem, the length of this would be how much? Square root of 2. And square root of 2 is a number, I mean, is a value on the number line. You can see that. That is, if I take the, if I construct that circle, so you can see that this new segment that I am making, excuse me, okay, oh, sorry about that. Okay, here. So from here to here, it will be the radius of the circle that we just used. And this length is how much? You know, which is very close to 1.4, but it's not really 1.4. And that length actually is again how much? A square root of 2. So you can see we have a square root of 2, a number on the number line, and it's an exercise for you to show that a square root of 2 is not a rational number. All right. So what happens? There are lots of, actually, lot more, or let me not go in that direction. So there are many numbers on this number line that are not even rational. So what we would do is that we will just take the set of real numbers, so as the set of all the numbers on the number line. Okay, and even in R, you know that this equation x squared plus 1 equals 0 does not have a solution. So what we can do is that because if you try writing solution of this, what will happen is x will have to be plus or minus square root of 1. Okay, and square root of negative 1 I meant, and negative 1 is not a real number. So what we do is that we just go ahead and denote it by symbol I, and we augment R with that, and then define our set of complex numbers as, or take our set of complex numbers as the set of all the numbers a plus bi, where A and B are real numbers. Okay. All right. So A and B are real. All right. Are real numbers. Okay. So let me not just bore you with this continuing descriptions and get on to some construction here. So now let's say we have A and B, two given sets. Okay, then we can define their Cartesian product. A cross B product we will just use the typical symbol for product. Okay, that consists of the ordered pairs such that the first element is in A and the second is in B. Okay, so say A belongs to A and B belongs to B. Okay, now so in this form you can take any two sets and form their Cartesian product. This is called Cartesian product. Okay, and then if we take a subset of this Cartesian product, okay, then that's called a subset, means proper or improper. Okay, so then R is called relation N. Okay, is called a relation. Okay, from A to B. All right. So for example, let's take A to be the set of residents of the United States. Okay, and let's take B as the set of real numbers, and we can define a relation by just as a subset of A cross B here. Okay, subset of A cross B. Let me just change those to mathematical notations. Okay, so we have A and B. So we can define a subset or a relation from A to B as that A, B that is in I, or A is related to B. Okay, if the element B stands for the income of the resident A. Okay, so just this is just a relation, as we will talk about in typical relationship. But however, we are going to just go ahead and work with our set of numbers. And again, in particular, mostly we shall work on the relations that are defined on the same set. So for example, if I have a relation in A cross A, we call it, or we call this R, a relation in A simply. All right. So here, say and you can also, instead of saying it that formally, okay, you may also denote it like A is related to B. Okay. And let me just, A is related to B if B is income of A. So same way here, we would just go ahead and define relationship between the two elements of the same set. So let me take an example. And as an example, how about we take our set of integers z, okay, and just take a relation, say, let me call it E, from, or rather in Z to in Z cross Z, that is defined by this. I'm so sorry. Okay, Z cross Z, where Z is the set of integers, where, so what we would say is that AB belongs to E, or A and B are related, okay, if say A minus B is an even number, okay, so is an even number. All right, so that's a relation in the set of integers. We can, so let me just call it example one, because we are going to discuss these further in the course. And we can actually, we can also write E as this, that is, we can just take it as that E consists of A minus B, where again E is a subset of Z cross Z, if A minus B equals 2M, all right, for some M in Z, all right, and we could write inside, or we have to mention here, that E is a subset of Z cross Z. And there is another way of writing it. Say this is a relation. So you may say that if we have AB in E, that is also denoted by that, by this symbol, that A is related to B. Okay, and again, that happens when A minus B is an even integer. And in the similar fashion, we can define another relation, okay? And say, for instance, we may say O, I just happen to take this symbol O, okay? And here, instead of even, we may say that, okay, it belongs to O if, one moment, if A minus B is an odd number. So here we defined two relations in Z, and similarly we can define relations in several different sets. The book has given you lots of them, and then we may let's just take some examples that the book does not have. So say, for example, say I take A to be W cross W, okay, where W is the set of whole numbers, okay, all right, or let me just write it down here for you, okay, so W is 0, 1, 2, 3, 4, and so I'm just listing it informally like this, and A is W cross W. Now I can define a relation, say, so say we have AB in A, right? Where A and B, both of them are whole numbers, okay? So AB, and I'm not writing in A because that's understood. It's in A, which is W class cross W. So AB is related to CD, and let's put a condition for that is this, that A plus D equals B plus C. Okay, so this is that two elements of W cross W are related if A plus D is B plus C. One moment, I made a typo here, and I'm not writing this in this form because here I will have to write this in the first component, this in the second, is going to get too crowded. Okay, so we just defined a relationship, and let me just say in A. Okay, that is those two elements of A and B are related. Okay, sorry, those two elements of A are related if A plus D is B plus C. And, in the same way, let me just take something like, let me just look for a symbol. Let me call it P. What I'm doing here is that I'm taking a set, just one set, Z cross Z star, okay, where Z is the set of integers, okay. So Z is the set of integers, and and Z star is again we can write it as this. We develop that notation that I just go ahead and take 0 out of Z. So what we have is that Mn, okay, they belong to P when if M and N are integers, okay, and N is not equal to 0, okay. And I'm not writing it really formally, okay, but you see, you know what we mean here, right? So we got P here. So here we may define that in P, let's define this, that Mn is related to, let's call it Rs, okay? So both these are elements of P, that is Mn are integers, N and S are also integers, but the only difference is that that N and S are what non-zero integers, okay? So if ms equals nr, okay? So that's the relationship that we defined here, okay? Or that's how we define this relation, okay? And let's take, another one. I'll just take a couple more because the book gives you lots of examples, and I just don't want to repeat the examples from the book. So here, let's take a set that the book has taken. That is, I'm going to take a set M such that here M consists of 2 by 2 matrices real, sorry, with real entries, okay? So A, B, C, D, where such that sorry, B, C, D, they are real numbers, okay? So if you take an element A in M, okay, or say if X is in M, then how does X look like? X looks like this matrix, okay? So means X equals, or big X. I'm just writing that as or nothing wrong in writing that as a small x, okay? Let's write, yeah, I'm still deciding. All right, let's continue with a small x. So, so here, that it's going to be, A, B, C, D for some real numbers, A, B, C, D, right? Okay, good. All right, so we have not defined a relation here yet. Okay, so let's just go ahead and define a relation. Okay, and then let me put this in one line. Okay, just change the font size a little bit here. Okay, so there we go. All right. So now I'm going to define a relation. And relation is easy to define when we go from relations to functions. And you have seen functions in calculus. Okay, then we will have more restrictions, but relations are kind of easy to define. Okay, I mean, have much more liberty there. All I have to do is, if I'm defining it in M, that is, that's a subset of M cross M, just need to stay in M. Okay. And now that I've shown you that this is one line, let me increase the font size because I'm going mostly by my vision. So here, X is related to Y if XY is what? YX, okay? All right. Now here you can see that I used this condition that xy has to be yx, and this is matrix multiplication because x is a matrix, right? And matrix multiplication, as you know, is not commutative. So here, two matrices are related in this only if they commute. Okay, so here we have a set of 5 relations, and that's kind of, or I'll define a sixth one in a moment. Let me write it down and then bring it back to you rather than you watching me type really slowly. So here we have uh, I mean, our set is, instead of taking numbers, I just took these 5 letters. All right, I could have taken numbers 1, 2, 3, 4, 5, but since I'm not using any numerical properties here, so that's why I just decided to let them stay as these letters. So there are 3 relations that I have defined. That is, in here, A is related to A, B is related to B, etc., etc. In this one, we have just like, one more than here. In this case, I have just expanded the same relation to this. And X has 5 elements, so X cross X will have how many? 5 times 5, that is 25 elements. Okay, so I just picked up a few to define these relations. Okay, so we have 8 relations to handle, and book has many more, and you can just go on Google and you'll find many, many, many more. All right. Okay, so let's work with these, and before I go to work on these, let's just go ahead and talk about a specific kind of relation on a set A or any given set. Okay, so now what we are going to do is that we are going to take up a specific kind of relation on a set X that is called an equivalence relation. So in this case, uh, well, let me first define it and then we will elaborate on the properties. So if we have a relation on X, say a subset of X cross X, we call it an equivalence relation if it satisfies these properties. First one is reflexive. That is, every element of X has to be related to itself. Then it has to be symmetric, that if X is related to Y, then Y has to be related to X as well. All right. And then it has to be transitive, that is, if X is related to Y and Y is related to Z, then X has to be related to Z. So let's see that which of the examples that we took, they satisfy all these 3 properties. But because in order to be an equivalence relation, I have to satisfy all these 3 properties. So let me bring the examples back one by one. So here we have example 1 revisited, and where I took a relation in Z, and it was defined by this, that A is related to B if A minus B, let me write if here, if A minus B is an even integer. Okay, so if we look at this, let me erase this because, so this was just elaboration so that we have some space to write in. So to check whether this is an equivalence relation or not, first we have to check whether take any integer, okay, whether that integer is related to itself. That is, whether for any a, doesn't matter which a we are taking, a is related to a. So answer here is yes. Why? Because if you look at a minus a, okay, then a minus a is 0, and which is even, right? So, so this is reflexive. Now, if we have this, now second part we have to check is symmetry. So say we take A and B, any two elements that are related. So what would that give us? That A minus B is even, right? An even number actually. Now, if A minus B is even, then it's negative. B minus A will also be even, right? Okay, so is also even. And what does that imply? That implies that B is related to, sorry, B is related to A, okay? So what we got here is, we got the property that, or verification that this relationship is a symmetric relationship, right? Okay, then here, just don't get confused between these two ones. This is the example number one that I brought, and I could have, let me just relabel them like this. Sorry to distract you. Okay, so this was verification of property number one. This is verification of property number two. Okay, now let's go to the property number three. So here, say we got A related to B, okay? So A related to B and B is related to C. So that will mean, now here I'm just, I think writing would be better. So that means that A minus B is 2m for an integer, and B minus C, say that is 2n. That's what we mean when we say that an integer is even. So this is one way of describing it, right? So I'll take a different letter here. So if I add these two equations, then on the left-hand side, b's will cancel. And on the right-hand side, what will happen? We can factor a 2 out. And then what it gives us is this, that b's cancel, that this equals 2 times, how much? 2 times m plus n, right? Which means what? A minus C is an even number. So what did we realize as an implication of all this? That if A is related to B and B is related to C, then A is related to C as well. So what happened here is that these guys are, that this relationship is transitive. So what we found is that E, actually I had taken the letter E for them being even, but it corresponds to being an equivalence relation, right? So anyways, so this relation that we defined in one, that A and B are related, if A minus B is an even number, okay, that is an equivalence relation. Now let us take up the example number two that we had, that A is related to B, where A and B are integers, okay? If A minus B is an odd number, right? Okay, so if we want to check it being reflexive, then notice this, take any A in Z, all right, or any integer, what happens? A minus A is 0, which is not an odd number, right? So what happens is this is not a reflexive, this does not satisfy the reflexive property. All right, it has to satisfy all three of these. So one of them is not satisfied. So right here, we'll just check that this is not an equivalence relation. Okay, all right. And then let's bring up more examples. So for 3 and 4, I'm going to leave it for you to check whether these are equivalence relation or not as an exercise. So let's take up number 5 for us to check, okay? So now I have brought the example 5 here to check. And what we have is that we got 2 by 2 matrices with real number entries. And let me just do this here. I'm just changing the notations here. Instead of X, let me call it alpha because I'm taking these. I mean, there's nothing wrong in taking that as X, and let's call, instead of Y, let's call this beta. Okay, all right, so here we go. So what happens is that alpha is related to beta if they commute via multiplication. So we got this, and then we got right this here. So even if I change the place of alpha, it is still remains the same. Okay, so we have to check whether this gives us an equivalence relation on the set of matrices. So notice this. You can see, let me just pull this back up here, that it's not really hard to check that take any matrix, okay? Alpha is related to alpha because if we multiply alpha with itself, okay, it's going to stay as alpha. Nobody's going to doubt that, right? Okay, so for any 2 by 2 matrix, that is true. So this is reflexive, okay? All right. So first property is satisfied. Now, if alpha is related to beta, then alpha is related to beta, that implies that alpha beta is beta alpha. Now I'm just like doing too much argument here, or just trying to do it too precisely. So that means beta alpha is alpha beta, right? Okay. And that means beta is related to alpha, right? So we have the symmetric property as well. Okay, so beta is related to alpha. Now we have to check for the transitive property, right? That, so reflexive symmetry is working all right, right? So here we have symmetry. Now let's check the transitive property. That is, if alpha is related to beta, okay, and beta is related to, say, I take a matrix, say gamma or gamma. Okay, all right, let me just bring the symbol down real quick. So here is our gamma here. So what we want to show is that if alpha is related to beta and beta is related to gamma, that means what? That we have, sorry about that. Okay, I'm just trying to save time on typing. Okay, so this, and what else and what we have here and we have beta gamma, okay, equals gamma beta, okay, all right, or beta gamma equals gamma beta, all right. So this is given. Now we want to check whether alpha gamma for any of these, to check if what? If alpha gamma is going to be gamma alpha. So now pretend that we just checked and checked and we just couldn't really make it happen. That is by any reasoning. So then what do? We look for examples. All right. And since, well, this is a 2 by 2 matrix example, and if I am as old as I am, this is not really too much work for me. So I can show you that I constructed an example in which you can construct as well easily, because I'm going to show you the calculations in which you will see that alpha is related to beta, beta is related to gamma, but alpha is not related to gamma. So let me take you to the example. So let's say we take alpha to be 2312. Now in this case, things get sometimes tricky. I mean, I can spend like long time with you trying to investigate, okay? But I shall try to make this thinking as kind of, you know, natural as possible, okay? Is that how do we come up with an example? Because say we tried many and it didn't work, okay? And say we do this, like if we try proving and doing many other ways, okay? And I am, so for instance, say I take any other matrix here. For instance, I took 2, 1. You can see very likely these guys don't commute. Okay, all right. So here you go. Multiply this here. Okay, you can see that the product on the two, you know, this AB is not equal to BA, or if you interchange their positions, you get different outcomes. Okay, now you can do this. I mean, so we have to make a choice of alpha, beta, and gamma, in which, as I said, pretend we tried directly and it didn't work out. So we can do this. As I said, I just typed, whichever numeral my hands went on, and they turned out to be not commutative. Now, remember this, that there is a special matrix, 2 by 2 matrix, that's what our kind of territory is right now. And that is 1 0 0 1, which plays a role of, what is that? 1 for multiplication, and that will be very important as soon as we take up our group, study of our groups. So we could do this, and this guy here, it commutes with everybody. So it's related with everyone, even if the two extremes are not related. So for example, let's say pretend we take beta to be the identity matrix, okay? And so then you can see that alpha beta, and I know you know that they are commutative, okay? So we have alpha beta equals, I mean, just multiply, and I'm so confident that you will see that alpha beta is this matrix, and even if I interchange the positions, it will stay the same. Okay, so beta alpha is the same matrix again. Okay, and so what did we do? We took beta to be identity matrix, and let's take gamma to be this one. Okay, so beta is this, and we will take gamma to be the matrix right here. Okay. Now you can see that beta gamma will have the same kind of relationship, because when you multiply that with the identity matrix, you will only get gamma. Okay. So you can see that either of them is just going to be how much, whatever we took gamma as, okay, right here. And then you see right here that we wanted to check if these are the same, and we can see that they are not the same. So what happened here is that here we just failed to satisfy, or this relation failed to satisfy the transitivity property. Okay, all right. So here, so this relation is reflexive, symmetric, but is not transitive. Okay, so let's just, for sake of practice, just look at the other few examples that we wrote. Here you can see this is the entire set, and this is the relation on there. Okay, so in here there are 5 elements, and you can see all of them are related to each other, right? So for 1, we are really good, right? Let's look for 2. In 2, we notice right here that BC is in R, okay? Or let's write in the other notation that B is related to C, but we do not have CB in there, right? So, but C is not related to B, right? So C is, so here, just a moment, right here, I got it. So C is not related to B. I'm sorry, I'm taking too long and looking for that symbol right here, okay? But C is not related to B. So what happens is, so here it was, or it is reflexive, okay? But it is not symmetric, okay? So what we got is that we got, so it is not an equivalence relation. So let's move on to number 7. So now let's look at number 7. We have the same set, okay? So again, for part 1, when we look for it being reflexive, you can see all the 5 elements are related to each other. So it is reflexive, right? Okay. And then for part 2, part 2, here you can see that, I inserted CB in there. So you have that, BC are related. Let me just go to our other symbols. B is related to C, and it's not only, I mean, we can say if B is related to C, then we can find out, or we can see that C is related to B as well. In here is just show and tell, all right? And I don't know why I'm talking in such a rushing language. Okay, from next one I'll be a little considerate, okay? So this one, let's go to 3. So in 3, what happens? These are the only, this is the only part in which we see a relationship between distinct elements, right? So you can see that we have this, that B is related to C and C is related to B. So who are on the extremes? B and B. And we see B and B are related, right? So here we have B related to B, and that's the only place where we needed to verify, because everything else falls in a different category. So what we have is that we have this relationship transitive as well. Okay, Now we will look at number 8 also, just to complete this part here. So what we are doing is we are going to check whether this one is an equivalence or equivalence relation or not. Okay, so again, for 1, we just have to carefully see that I didn't drop anything, and I did not. So every element is related to itself. So yes, it is reflexive. Okay, and then for part 2, well, BC shows CB is in there, and if AC is in there, then CA is in there as well. And we can just, do an observation and check that this is symmetric. Okay. Now for third part, if BC and CB are there, you can see BB is there. And also if CB and BC are there, then CC is there, which I missed looking at in the previous example. And same with this, ACCA means AA is there. Or if we take CAAC, then that will show us CC is in there. Okay. But for transitivity, uh, yeah, that's what I was trying to see, for transitivity. So here, if we have BC and let's look at CA. So we have in here, B is related to C, and what we have, C is related to A. But we do not have BA in here anywhere, right? So we will have B is not related to, now I know much better where that is, but B is not related to A. So what happened is that we did not get transitivity here, okay? So your book, it gives you lots of examples. So you can go through that. And what we would do in the next presentation is that we are going to go through equivalence classes just to see that how an equivalence relation, it partitions a set into disjoint classes. All right. Okay.